Now, let me, after having this a recap on IWRM, let me just quickly now go into modeling in IWRM. So I have to mention that it's not just about modeling in IWRM, that perhaps we get a different modeling and approach and all that. I have to say that, I mean, it's the same modeling, because I think in the IWRM, I think I've looked at the lectures by Miriam and all that, even Professor Cosmo. We're looking at hydrology, really, and we're looking at water balance. Okay, so it's indeed the same concepts of water balance and hydrology on the other side, and that we bring it to IWA. But what is critical now is that how do you really bring the concept of water balance and hydrology into onto the table of IWRM, where you've got actually different actors, and that's really an issue, and this is where we need to look carefully on how we really deliver into that. So modeling in IWRM, I mean, as you've already noted on my background, is that it represents interactions between humans and the environment, and therefore it has in common, much in common with socio-ecological systems modeling, as well as we these days we actually have social hydrology. I'm glad Prof. Cosmo actually introduced some of these things. um, so the social ecological systems modeling, and so these, I mean, it's a whole lot of modeling in all that, but often focuses on the sustainability. I think looking at the Ostrom, for example, that was very key in terms of sustainability, but also the resilience and also the social hydrology. Is really looking at human water system interaction, and this is very key, because you see, when we are looking at modeling in water resources, as we're looking at different actors, and therefore we're not really looking at hydrology only, but we're looking at the social part, because we've got humans involved, but also they're very different, and in the way that you bring these people together, it's indeed kind of like a social. It has really a bigger social part of it. And IWRM, as I've already mentioned, so is underpinned by the water balance on the other side, and the hydrological modeling on the other side. So actually the water balance that we have, so we can have catchment A, for example, and what we're really interested is how much water do we have in a particular catchment. Okay, so if we have this water catchment, we know, I mean, water, and we know that we're going to use these hydrological models to tell us, we can actually borrow a number of parameters from the hydrological modeling, and then we combine together. Really, it has to be adapted to a specific policy or a planning setting, and then therefore this is the reason why I said sometimes these are really context specific, because we have to use the water balance ideas, the hydrological modeling, but then it has really to fit in a particular policy or planning, because IWRM, honestly, it is really looking all across, and how you plan, but also how you really implement. Um, Now, modeling in IWRM. So yeah, in this context, so a model, as we all know, so it is an explicit representation of features and relationship of a target system. So in our case, we could actually have a catchment, for example, and we might be interested in one way or the other, whether water allocation, whether we are interested in knowing what are the impacts on water resources, whether in terms of the availability in the longer term. We could actually be we could have several drives in terms of uh, what what drives us to do a modeling, and therefore there are a number of models. I have to say, I think maybe Prof. Ngongondo mentioned already some of these models, but they're very different kinds of models. Some of those are process ones, some of them they're physically and behavioral based, some are gaming, the actor based, conceptual, or even a flow chart, because we're talking about in the framework of IWRM. And each of these models, I know they have got a range of characteristics, such as is it static or is it really a dynamic model that it changes. So again, it depends on what you're really looking at. I might actually the example that I'm going to give in a second lecture is looking at a system dynamic modeling, uh, but that you can actually even apply at a catchment level as well. So we're going to look at that, and it can actually be this model can also have a statistical or empirical or indeed probability. I mean, it's very very important in hydrology. We're looking at the probability because what we get is the data for today in time and space, but I mean we can actually project this, so. And it can as well be a distributed or lumped parameter. I know we have you are aware about this, so lumped models or distributed models, where you have a parameter that you can actually say, okay, this is an average for this catchment, or rather you've got several of them. So IWRM, as it is, it can utilize any of these models really. So it's really that how you use it, but in terms of whether that model is informing the policy or the planning, what you have. So there are challenges also for the use of modeling in operationalization of IWRM, and this is the reason why I had earlier presented on the critics of IWRM, because the same critics that we have at IWRM as a concept or as an approach, it can actually bring problems when you're actually trying to model it. Yeah, and indeed, these two key thing is that the difficulty of managing wicked problems in water policy, where there, you've got actually multiple pressures. You've got conflicting stakeholder values. You've got competing goals. You've got multiple decision makers. You've got limited resources on the other hand, and you've got also deep uncertainty. So really to come up with a model that would say, okay, I have actually modeled the water resources allocation and all that, and this is a fit. I mean, you might actually find to say, yes, for example, I might be interested in water, but maybe water for food. I might actually be interested, but maybe water for energy. I might be interested in water, but maybe for industrial. And so these are really wicked problems, really, in terms of IWM, or rather in terms of water resources, especially allocation and planning, because you've got a different actors, okay, and then you've got different users of water, and this is very very important to understand as we model, because what we model today, we can say, well, it fits for catchment A and for these particular users, but it may not really be fit for for users, maybe category B of users. So those are the challenges that we really get when actually when we go into a modeling of these of IWRM and water resources allocation, and also the handling of the human element in IWM, and the reconciling of the conflicting agendas involved in water resources management, and that is really also in line with, it's just by the extension in terms of how multiple users are, and you really have these challenges in terms of modeling IWRM. But a number of scholars before, I think they've tried to kind of like provide a step-by-step modeling approach, which we can say, while it is perfect, not it's not really perfect, but because these are really depending on a specific problem or area, for example. And so there are several phases and steps in IWRA modeling, for example, and and I think this is not just IWRA modeling, because I mean any modeling exercise or work that you would want to undertake, it will actually comprise of all those stages. So these four stage phases, for example, you've got the planning phase, you've got the development phase, you've got the application phase, and then the perpetuation phase. Just going to look into details just a little, um, uh, just a minute from now. So all these phases, if you are a hydrologist, for example, and we do know that when we want to develop a water resources, for example, I mean a model, we have to do the planning, the development, and all that. Yeah. And so the planning stage really. is looking at when you're planning a model. So what is to be achieved? Because I think that is very very key. What is to be achieved? And really, that question is not as simple as we might actually look at, because then we should be having in our backgrounds that we have got different users, and so what is to be achieved? Okay, what do we need? Are we trying to allocate water? How is it equitably or not? Or who gets more water and all that? So what has to be achieved has really to be defined in the planning stage, and how it can be approached, and what are the sources required, and that's very very key. And then you can actually have a key steps. These problem identification and scooping. Perhaps we know those things already. Stakeholder planning and project management planning. Also, the preliminary concept model. Because when you understand the problem or the context, then you can actually conceptualize to say, okay, I think this is our problem, and I think we can solve it that way. And then you have like uh, as a start in terms of modeling. And then the second part indeed is developing the model. So you kind of like build a model, you test the model as always has been, and then the key steps really is you have learned to do the data collection, the construction of the model, and then model calibration, as we all know it. For example, the uncertainty analysis, testing, and evaluation. Um, and then the second stage, the third stage rather, is application. So that's when you've built actually the model. So these are now you have the model in the development stage, but then you apply it. As you apply, and most of the times we know that in the hydrology or indeed water resources planning, so we need indeed to experiment, we need to analyze and visualize, but also communicate the results to the users, because that's it. Because I mean, you cannot just produce a model in IWRM without really the end user. So you really have to communicate the results. And the final step, really, and then again, it could be the final slide in my first presentation, is the perpetuation. So really, this depends. I mean, if models have become part of the ongoing decision making or policy or process, yeah, and these can be perpetuated. Actually, you can actually, take it further. You can actually document, you can actually process evaluation, but also you monitor, but also you even upgrade it. For example, if you feel like the model works for you, and if it works for you, then you would have actually basically say, okay, fine, I think we can actually take on this model, or maybe we can develop it further to make sure that people can use. So that's just an overview of the modeling in terms of IWM, as I've mentioned. So we basically use the same models. There are a number of models, I have to say. Actually, there are many. I'll share the second presentation, where I'm looking at system dynamics modeling, and I think I may not have shared, but I think after the talk, yeah, you are free also to contact me if we can even arrange. I'm not sure we can. Prof. Ngongondo can as well guide that at some point I can actually uh, 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 demonstrate how the modeling that I'm going to give you, how it works. I'm very happy to do that, and that you can also have a hands-on and all that. So that's a system dynamics modeling. I'll tell you why it is also very very good in terms of IWRM. So this is the first, and I'll stop sharing these slides, uh, and then we'll go to the second presentation. But whether people they have questions now pertaining to this presentation, you can let me know. I'll stop sharing. Okay, so I'll just fetch a second presentation. Okay, so if you are able to see that, just give me um, a shout that you're able to see my screen. Okay, great. So this second part, it's an interesting one. I really like it, and I think Prof. Cosmo knows I really like this. And basically, I and Prof. Cosmo, we are working on a certain project. We're looking at the basin closure project. So where we're looking at if we look at a catchment, and then we see so this is really an IWRM kind of like a project modeling. So we're looking at, let's say, for example, in a catchment, A, for example, and we are saying, let's say for today, how many, how much water is being abstracted. So we're looking at both surface water and groundwater. So we're looking at all those abstraction, the water rights that you get. And then we are factoring in the climate change there. So we get the weather data and all that. But then we're looking at the total water available. And when we've seen that, then we would want to project it with the population, for example, in, let's say, in 10 years, in 20 years. So how will it, in terms of the demand, for example. So again, it's a bit it's about water balance. What do we have in a particular catchment, and what is our demand, and how do we really balance that? And we would want really to classify these catchments whether in 10 years times in 10 years time it will be able to provide water as we are being provided today. And remember that in IWRM, I think the issues that we really emphasize is about sustainability. I mean, if a catchment will not be able to provide water next year or the other year, and then it's a problem. And therefore, for us water resources professionals or practitioners, we really need to take a step. Either it might actually require that we need to do catchment conservation and all other steps, or we can actually do demand management of water resources, for example, because we would want to avoid, let's say, for example, the case of you remember Cape Town, where it had reached day zero. I mean, like, you really afraid that you may not really get water anymore. So we call those catchment, or rather basin, closed. Okay. Or when we say a basin is open, that means we can still get water from a particular basin. But when it is closed, then we can't really allocate more water to users, and that's very, very key. So we are doing this work, and we're using a number of hydrological models, of course, but anyway, we are also adding the system dynamic modeling. So this one, I'm not sure, maybe Prof. Cosmo or any other leading the course, we can basically, I mean, we can arrange with the students, and so I can actually provide an in-depth steps into doing the system dynamics modeling. Because what I'm going to do here present now is just giving you an example of how problems that you can have at a catchment level, at a basin level, and how you can use system dynamics modeling to solve such kind of problems. Yeah. Um, so okay, and then I'm going to give you kind of like two I should say two examples in terms of I'm going to provide also the WEF nexus kind of like an example. So yeah, the system dynamics modeling. So the motivation really is that daily life and the development of our world are determined by complex, coupled dynamic systems, and this we know, and this relates very well to IWRM, because IWRM is complex because you have different stakeholders. You've got different practitioners. You've got different, I mean, scientists who specialize in different things, and our problems really are very, very complex. Okay. So you talk about people, animals, plants, technology, enterprises, and all that. So it's really complex these days. I mean, if people in catchment A, they say we have a problem in terms of water quality, you may not just say, okay, it's one thing. So you might actually go there and find that these are confounding factors that are leading to the water quality problems. Uh, but also the system dynamics is an approach to understanding nonlinear behaviors of complex system over time using stocks, flows, internal feedbacks, loops, and all that. And this is very, very important, basically. So in a normal setting, we would want to believe to say if Bright, for example, has caused uh, this kind of a problem, perhaps Peter or Cosmo, this is what they are going to, to react, or if or they're going to react to that and all that. But most of the times, I think we viewed our problems, or rather, in the way that we model things, in a very linear form. Like the A causes this event, and this is how one reacts and whatsoever. So in a very linear form, that we are going that way, that direction. But I think we've known now. I mean, IWM has also taught us to say, I think it's not really linear. Uh, I think these issues are very non-linear in nature. For example, I mean, if I want to abstract water, for example, and I apply maybe, for example, to the government, whatever, let's say, for example, in Malawi we've got National Water Resources Authority. I'm not sure in Namibia you've got the authority as well. If you apply and then you get a license to abstract water, you can be given Q. Yeah, so you can be given the volume of water that you have to be abstracting, but you see that volume, it has impacts both downstream as well as upstream. Okay, if especially, for example, if you're constructing a dam, we know that it has impacts in both ways. Yeah, so it's not really just linear, that I mean, you get water and that's it. No, our problems really, they are very, very non-linear. Issues to do with water quality, as I've said, there are confounding factors that lead to that, and that's very, very key. And so the system dynamics modeling really helps us to solve that. And again, in IWRM, so we've got different players and whatever, how they think and all that, it's a bit different. There is another kind of modeling. I mean, agent-based modeling is also quite different, but again, it's very, very fitting in IWRM because you've got different people. So as I've said, so most real world challenges are nonlinear. I mean, Abed et al. They mentioned that, and not fully addressed by linear thinking. I mean, we can't just say we're going to do A and B in a linear form, but what we do basically can have feedback loops, or rather can have other impacts or on what we do in one way or the other. Yeah. So we are dealing with complex system. I mean, uh, if you look at the picture on my side, so I've given both. I mean, the surface as well as the ground surface, for example, whether we're looking at groundwater. But this is just an example. I mean, we could have an example completely looking at the watershed. I know that you had those examples before by Prof. Miriam. I mean, you've got all those complex in terms of a catchment, for example. That is really complex. If you follow it up and all that, it really needs a careful analysis and all that. So, as I said, so the complex challenges require really complex approaches. So, in river basin, we've got. I've mentioned already this about multiple uses, and so the planning also, has to take note of that. And system dynamics models are one of the groups of tools being used in studying multiple water use and planning. Okay, so the multiple water use and planning, already then we are talking about IWRM, and so there are a number of tools, colleagues I've mentioned already. There are a number of hydrological models. There are a number of tools that you can use: the agent-based models, actor-based models, and all that that you can use. It really depends. The modeling steps, or rather the phases that I've mentioned to you. So you define what you really want to achieve, and that's very, very key. So system dynamics modeling. So I'll just call it SDM. So it's able to model complex systems whose behavior are nonlinear. And Garcia actually wrote a very good book there, and there's got a number of actually articles relating to system dynamics modeling. I would encourage you to go and actually read about that. And system dynamics is different from other approaches to studying complex system because of the using feedback and all that. So just the figure on the other side, so it's telling you to say, I mean, basically we know that we when we have in terms of the balancing is the is for example the normal equation, we know the in and then we get the out and then we get the change in storage and all that. That's what we know. But then you can have actually a number of variables that would come in there and then the feedbacks and whatsoever. So this is where I mean a system dynamic modeling will really be helpful to do that. So I'll provide one of the examples in terms of water allocation, and these are the challenges that we have at a catchment level, for example, or in terms of water resources modeling or IWRIM. So one of the idea that we have, I mean, and I can share this paper. We published this paper in Journal of Physics, Chemistry, and I think I can share with all of you. You can actually look at how we did the modeling, and as I've mentioned, that we can actually even have a session. I don't know in the near future where I can actually just look at. The system dynamics modeling using the VNCM. So perhaps I would allow you perhaps to read first, for example, and then at some point, the course leaders, they can actually say, okay, this is the time now. You can actually offer the sim modeling, which is system dynamics modeling. So idea was, the challenge was how do you really allocate water resources? And this was at a basin level. So this basin, we took it in Zomba, in Chingali. So the issue, well, I'll explain about that. But indeed, the main objective was to develop a simple decision support tool based on system dynamics modeling to support water allocation decision at a small scale in Malawi, basically. And we use VenSim. So VenSim is a free software. Uh, I know Prof. Cosmo mentioned about these free softwares and all that. Indeed, there are a group of people that they're really interested in making sure these academic or research-based tools they could be free, so everyone can use. And indeed, VenSim is one of them. Is a very free, and you can download it. uh, we actually even have a society we call it system dynamic modeling society, and it's there. It's world global, and I think it's very important. If somebody is interested, you can actually join that. So it is an interactive software environment that allows the development, exploration, and analysis and optimization of simulation models. So this is really looking at simulation modeling. um, and okay, so because our idea was in this case was we had a challenge. So we have farmers who are very interested in fish farming. So they have got ponds, and but also they've got a piece of land. So ideally I was like, okay, fine, can we use the same pond? Because a fish, the way fish will maybe take some time, and I think some of the water they just stay there and all that. So can't we really use the same water at a very small scale? For example, of course, this can be outscaled. We can get water from the pond and irrigate, for example, a particular land, and then vice versa. So, for example, we could actually get some uh, leftovers in the farm and then put it back in the pond. So kind of like a secular economy kind of there. And can we do that? And so therefore we use the VenSim in terms of system dynamic modeling, but we use also the fowl aqua crop model to kind of like look at the crop growth. So simulating the crop growth. Yeah. So we use those two. And I would say so. This is the setup. So as you can see, so we have a fish pond, for example, on A, and B we have a maize crop. So idea was, can we get water from the fish pond and then irrigate this crop without really, having issues. I mean, getting too much water from the pond and all that. So we were looking at really optimizing. So, for example, a rural farmer, for example, may not know to say how much water I should actually be applying at, and all that. We know what irrigation demands and all that. And then on the other hand, they need to make sure that they still have enough water in a pond so that they don't really uh, um, affect the fish growth. So that was the idea. And we said, well, I think we can use the system dynamics modeling to do that. And what we did, we collected data. So if you look at the steps that I mentioned, so we planning and all that, indeed, then the data collection. So we looked at the rainfall maximum, of course, the usual rainfall, temperature, humidity, sunlight hour, wind speed, and all that climate data. And then the flow data we actually had to measure um, from, because there was a huge canal just passing around, which was getting water from a river, which was a river diversion. And that, yeah, so we looked at also the hydrological part of it, just looking at the bigger catchment, for example, but at a small scale. I think we're just interested to look at the river, how it flows, and how much water we're getting from the river to the canal, for example. And so conceptually, we designed this kind of like okay. So we have a number of components which are very very key. So we have one, we have a pond, and which actually provides water. So if we've got a pond, that means we have to look at the water balance. Okay, we really have to balance this water. How much water goes to the field, uh, and how much water remains in the pond. Okay. At the same time, which is linked to the same pond, that means we've got fish growth model. So how does a fish grow, for example, from all those stages? And I think if you can look at this again, this was an example of IWM. So I am a hydrologist, but then I have to call somebody who's into fish, for example, to understand how the fish will grow and all that. And so it was really a kind of like much stakeholders looking at this. And so at the same time, as we're looking at the fish, then we've got to irrigate. So if we're going to irrigate, then we've got two issues. And then we have actually soil moisture uh, that we have to maintain at each and every time. And that is dependent on the crop water requirement. Okay. So which again is a crop growth model. So if you're using whether you're irrigating maize, so in this case we're using maize. So you can have maize, you can have other crops, and then the growth model characteristics are actually a bit different. Okay, and so where and that will have even an impact in terms of the soil moisture that you require, and that will actually have an impact of how much water at a particular day you are getting from the fish pond. Okay, and having built that, I'm sorry, so this is yeah, so if we as I've mentioned, so I think the course leader can actually take note of this. So if you're going to download Vencim and all that, I think we can actually go through that at some point. I didn't really prepare that for today. I just wanted to introduce. Uh, but if we do that, really, I mean, if you go into the system dynamics modeling, having, let's say, for example, a step by step, producing this, if you create, so there are a number of more equations that you indeed have to do. Unfortunately, I cannot zoom, but you can have several models. So, but what is key here is that uh, these same key components here, because these they have to relate. For example, the soil moisture, the crop model, the water balance, and the fish model. And from this, what we're getting really is the total productivity. So we are really interested in terms of the, for example, the tonnage, the yield of uh, maize as a yield after all that experiment. But I think what was also very, very interesting was the fish crop model. But I have to say that we didn't really develop the fish crop model fully because I think it needed the nutrition and whatever and how it varies. So this one we really didn't do, but it was a component that basically we are looking at trying to fully fully develop the fish model, and then it can work, as a whole. So what you see here basically we have the pond water, we have the water balance, and then we have the fish, rather the soil moisture and how it interact. And I mean, as you can imagine, if you're looking at, for example, the crops, so you've got all those the crop characteristics growth. Let's say, for example, you need to look at the wilting point. We're looking at field capacity because you're looking at the soil moisture, and there are a number of actually variables, and I think they are actually contained there, as I've mentioned. So I'll provide you the full paper so that you can actually have a look at it, and it also can actually provide a little bit of a basis of how we do system dynamics modeling. um, yeah, so the simulation results were quite interesting. So we had the pond water depth. This is how it was actually doing. So we looked at the period. I think the period, because we wanted maize. So maize has got that limited one. So at first we could have that, but then it was changing. That means those changes is because water was actually being abstracted uh, from this dam. A simple dam is you can actually think about, and it was being taken to a small field of maize. Yeah, and the crop growth that's the graph there, which shows again that it was actually just growing as we would have expected. And yeah, so basically the results are the key parameters were successfully simulated, because in system dynamics modeling, and indeed in IWM, you can really get if you have not really developed a very good concept, and then build that into, you can develop a model, and you can have really issues in terms of simulation. So it may not simulate, it might give you a lot of errors, but after developing that, building that, we found that it really simulated very well. And indeed, the pond water depth we maintained now at 1.5 or 2 meters. So this was based on the research in terms of the fingerlings, for example, the fish growth. So it's really required that we have to have 1.5 and 2. Those are the depths that we kind of like controlled. And then the maize use was quite good. And then it also was reflected. But remember that this was a really that we looked at it very well. So in other ways, in terms of fertilizer, in terms of everything, all those agronomic practices, we really followed it very well. We know that this can really vary because, I mean, there are a number of factors. And this is the good thing of system dynamics modeling. So you can actually include a number of models there, I mean, components, depending on your problem. And this is true because I mean, with other water resources modeling. So water resources modeling or IWRM, there are a number of issues that actually, they come into play. For example, we could have a problem where we are saying we would want to allocate water for a particular, I mean, for a particular catchment, and there are a number of um, for example, user, how do we really allocate that water, considering the hydrology part of it, and then the water use in the long term. So you can actually use a system dynamics modeling as well. And I would really invite others, if they've not really chosen their research topics, for example, or rather the way they are going to work on this, maybe to utilize the system dynamics modeling. And I think it's really good. It's fun. You may actually need to try it. Yeah. The second part that I wanted to do is the WEF Nexus. So this was the work of a colleague who's looking at water, energy, and food nexus. This is really an extension, but I think I'm not really going to dwell on that. But I'll provide both all these slides. But again, here it's just looking at, we've got these hydrological models, which are very useful. They provide evidence of viable alternatives. Okay, so hydrology actually revolves around water, but we are in a changing environment, as I've mentioned already. So we are really changing, and therefore we have these integrative resource management. So we're looking at WEF Nexus, for example. It really looks at it's a concept. So basically there is now a talk, basically, and this is the reason why I gave this talk. So if you follow, if quite a lot in terms of IWRM and also the WEF Nexus. Actually, people are saying, well, I think the WEF Nexus is just is just a continuation of IWRM, or rather, yeah, always a replica of IWRM, or really, if we can really tighten up, maybe we can actually be using the WEF Nexus, because the WEF Nexus, how related it is because it also considers that, see, okay, you cannot only plan for water, or you can only not plan for energy, or you can plan for food, but these things are interlinked. And I think it's the interlinkage and nature of it that really talks back to IWRM. So ideally for the wave nexus, they're saying, well, we don't need to look at one problem as it all, but we have to look at the synergies. In other words, the synergies are what are the benefits that we can get from one sector to the other, or from one use to the other, and that we have to minimize the trade-offs, whereby you say, um, if you take so much water and you disregard any other things, you might actually have impacts on the environment. And yet, if you don't really consider that, it can be a challenge, and that can be a trade-off. So we really need to limit that. And indeed, this stakeholder involvement, I think this one I've already mentioned in the IWRM. This was just kind of like an example. And indeed, that we have to have inclusive problem solving in the WEF Nexus. So it has also steps which are very, very similar to IWRM. And that so yeah, the concluding remarks indeed is the same. So if you can look at it, is really looking at yes, we can't just be working in silos, which is like, for example, if you can't just be working as individuals. I mean, rather in a traditional way where we're just focusing on one use and whatsoever, but now there are a number of uses that you can actually have. um Colleagues, I have to stop here. I know I've talked for quite a long without really stopping, but yeah. So this is really my short talk to you about modeling in IWRM. So the first one was just really giving you an overview of IWRM, a modeling in IWRM and its challenges, and I've just given you an example that you can do. So they, as I've mentioned, so this is not one of them. I mean, this is not one the only modeling tool that you can use. There are several actually tools that we can actually use in IWRM. As I've said, I think the course leader can actually will actually guide, but I'm ready. Also, I'll be able to provide all these slides, and I'm also going to share you the paper that I was just talking about system dynamics. I really want maybe one or two can be interested in system dynamics modeling, and at some point, I don't know when, but we can actually plan that. I can actually go through the VenSim software. There are a number of also system dynamics softwares. Yeah, that we can use in terms of modeling. Yeah, but I've just shared you this one. Thank you so much. I'm not sure if there are questions, and I think that will be the time now that we can talk about it. I will stop sharing now. Yes, Dafila, yes.
Good morning. Good morning, Dr. Brighton Chunga. Hello, are you there?
Yeah, I can hear you. I can hear you. Please just speak up.
Hello.
Yes, I can hear you.
Oh, okay. Well, there was a glitch on my end.
I
Thank you
noted so as
for
well.
Yeah, all right. Thank you for your presentation. And I think most of it was tailored to one of my objectives, because I
Oh,
actually,
okay.
sorry, to one of my, yeah, I have an objective on performing a system dynamic modeling in my study area. Just an overview. I'm studying groundwater surface water interactions in the Okavango Delta, looking at the sustainability of the ecosystem itself and the livelihoods of people around there.
Ah, great.
Yeah. Yeah, so I had proposed to employ system dynamic modeling in order to determine the effects of hypothetical scenarios that are bound to happen, as well as those that are actually happening both in situ and ex situ of the delta. As an example, we have maybe an ongoing oil and exploration upstream the delta. There could also possibly be developments in Angola or Namibia that might actually be detrimental to the amount of water that flows into the delta. So I was wondering whether it's an ideal application to say, can you model hypothetical scenarios? For example, one of the hypothetical scenarios is that there are plans of damming that river system in order to produce hydroelectric power station, but it's not yet in place. It has been something that has been discussed in some EIA reports.
Yeah. Tafila, am I losing you?
No, I'm here. Sorry for that. There was just some disturbance from the alarm in the office here. Yeah.
Okay.
So one of those hypothetical scenarios is that there could be a possible damming there. So I was wondering whether system dynamics modeling could actually give an overview of what would the water resources look like if there would be maybe abstractions upstream or damming of such.
Hmm. Yeah, I mean, it's very very possible. So I think one thing that I didn't mention is that you see the system dynamics modeling. You can as well imply these questions of what if, what if questions. So
Oh, okay.
yeah. So for example, it depends on how you build the model, but then you can ask to say, for example, what if we are abstracting, let's say, uh, x volume, and what will be the implication? So you can actually put that a what if question, and then you can see the system. It can run depending on the time frame or that you've actually put, and then you can change a number of. So you can run a number of scenarios. So in other ways, system dynamics modeling is also very good in terms of scenario analysis or scenario performing.
Oh, okay.
Yeah. So I think
There was one question I asked a professor who was presenting something on a system dynamic modeling. I think you're also bringing that point here to say you can actually say how much if you extract maybe X amount of groundwater or something. But my question that I thought maybe it was not answered from there was, are you able to combine quantitative and qualitative data sets in a system dynamic modeling? Because my thinking or the few literature that I've read, it seems like it's geared mostly on the socio-economic aspects. But now coming from a technical point, you'd probably be having shape files. You would also be having values that you can put up in the system, but some of these hypothetical scenarios, you cannot actually tie a figure to it. How is the stability of this kind of approach, where you do not have maybe say actual figures, but of course, if you do something, it will maybe cause a reduction of or a certain variable within your model.
Mhm. Okay, so you mean like in some cases where you really don't have figures, or it's just hypothetical.
Yes.
Is it a way of I mean, I know that that could be a challenge. I know that system dynamics, you can actually have these dummy figures and all that. But yeah, I think most of the time that the way that I've worked, of course, is that you kind of like it works on indeed quantitative data, but sometimes you can actually have a dummy kind of like a proxy for the qualitative data. um, but I maybe I have to look at if we how we can actually use. I mean, if something is purely qualitative, for example.
Oh, okay.
Yeah, yeah. But I mean, I can check, and then I can
Hello.
actually come back.
Yeah, I was now thinking maybe we can also have a discussion beyond this class.
Yeah, sure.
Just when
Yeah, I'm very open. We can actually have that discussion, and it's interesting actually for your case. I mean, it's really. a very good example where you can actually you have got these mad curiosities and whatever, and then you use the system dynamics. I'm really glad. There was one actually, so I'm not sure where. So which university are you?
Namibia University of Science
Ah,
and
oh, okay,
Technology.
because I know we had a student together with Prof. Kanyerere, I think at University of Western Cape. I think was looking at the interaction of surface water and groundwater. But I think it was not looking. I think it was more concentrated on groundwater, of course.
Oh,
Yeah, but
okay.
Fila, yes, we can continue to have this discussion maybe even beyond this after this.
Yeah, may I just kindly request you to type your email in the chat, please? Then I can drop you an email
Okay.
there.
Okay, okay, thank you. I will do that. There is another hand. I can't see who is it, but I've typed in the chat my email address. There is another hand. I don't know who.
Yes, good morning, Dr. Bright.
Yes, thank you.
Yes, this is Muyaka from University of Zambia. I'm sorry I came in a bit late, but I got a glimpse of what you were talking about. I was mostly interested in one of the case, which looked like an hydroponic, aquaponic system, and I believe that it's also within encompassed within also what you're calling as a system dynamic modeling. I just want to understand something. What are the pros and cons of the system, which is aquaponic, in the sense that you've got water in a fish pond, and then you use that water perhaps to your plants and things like that. What are its pros and cons, and from case studies? What can you say about that system?
Okay, so I think you're talking about the pros and cons, for example, in the study that we did, right?
Yes, I don't know if I'm correct, but one of the cases I saw something where you're talking about is it a fish pond where you can use
Yeah,
that
it's
water?
yeah. So yeah,
Yeah,
so we use a fish pond, and then we took water from there to the farm and like that. Yeah, so that was the system.
yeah. So that's what I
So
was saying, that kind of a
the
system.
setup, yeah,
Yeah, that setup is known as an aquaponic system, where
yeah,
you're using water from a fish pond and then you're putting it into plants. I
yeah,
was just wondering if you've done many case studies around that, and then what kind of pros and cons come in from that, and how
yeah.
efficient can
Okay,
it be used? Yeah.
yeah. Thank you so much. Thank you so much for your questions. Yeah, so we did it at a small scale. Of course, we're trying to kind of like outscale now. Uh, but the challenges that we really got, well, I mean, the positive, of course, is that we were able to simulate and
Sorry,
that
just to interject you. Where exactly did you do this?
this study. So this study was done in Malawi, in Chingale,
Malawi.
somewhere in
Okay.
Zomba. Yeah.
Okay. Sure. Okay. You can
Yeah,
proceed.
sure. So, ideally, it's that okay. So we were able to simulate. I think that we would be able to we would be able to tell the farmer, okay, you can now actually just open your dam and because because that was another thing. It was a decision too. So, for example, to say, okay, when you just wake up, you can just open water, and when this water reaches here, you stop and whatsoever. So it was very nice that we, at the end of the experiment, we would just actually put, uh, 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 you know, sticks, and then we can just say, okay, you open water up to here and whatever. So it was really, really successful in that way, and in terms of also fish crop. I mean, rather the crop growth. But what was very, very daunting, really, I think, in the setup, I think, was in terms of and the resource use. So ideally, in the full-fledged system, we thought we could actually be getting, let's say, for example, in the aquaculture, you have fish feeds, and then they settle down there. They kind of like mud, they degrade and whatsoever. But you can actually get the same and use it as a fertilizer in the maize field. But I think we're not able to do that, but because fish, for example, I'm not a fish specialist, but I understood that they have got their own, specific environment. You don't just have to disturb and all that. And so I think that was the only challenge that we had in this case, and that we could actually not really fully build the fish model. I think that was the really challenge. But otherwise, I think everything worked fine. I think if people are well trained and they're told to say we are going to get this data and all that, I think it was quite a success. The only challenge was how you need to model the fish fully. Yeah, but otherwise, I think I didn't really have those big challenges. But maybe if we kind of like now uh, uh, fully, let's say in a bigger catchment, for example, that would be an interesting one, especially what is it Tafila is doing. I think that would be really an interesting where we can actually now look at what could be the main challenges that we have. But as usual, I think I can mention to say the issue of data, I think in Africa is really an issue. And so we always have problems because you have to look at met data, for example. I mean, always as it has been in hydrological modeling.
Sure. Do you think it's scalable to large scale, though?
So this is what we are doing now. So in Malawi, so where I work at Mzuzi University, we have got a fisheries department. So we've got specialists in and fisheries. So we want to try it at a large scale. And see how it actually, because especially now we would want to concentrate on the fish model, whether we can really, and so this will be longer term because, for example, I think to track, let's say the fingerlings, that's the fish, fish kits, whatever, the fingerlings until it grows. I think it takes a little bit of time. So we're trying really to scale this up. Yeah. But I think in terms of the modeling point of view, it's very possible. But I think we need to have to go on the practical, I mean, on the field and see whether this is can be scaled on a bigger scale.
All right, sure. Thanks a lot.
Yeah, so I'm not sure. So I've typed my email address. If you can, I think everyone have seen it. Okay, good. So yeah, I end here if we really don't have any questions. I'm not sure whether Prof is around, um, or any. I'm not sure who's the course reader. Uh, I'm not very sure, colleagues. I I just know Prof Cosmo Ngongondo, but I think he's away. Is any course leader available?
It's the filler.
Okay, it's Tafila. Okay, fine. Okay, good. So Tafila, maybe if you can send me a short email, and then I can send all these slides, but I can as well send you the paper that I'm talking about.
Yes, I have already sent you an email.
Thank you so much. I really appreciate. So yeah, thank you so much, colleagues. I'm sorry that it has been very short. It's Friday, but yeah, as I've mentioned, so Tafila, I think you can.
Yeah, so colleagues were online after receiving yeah, 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 I was just saying after receiving your slides, I'll pass on them to Dr. Mabugu, who will distribute to all the participants because maybe some are not in today, but they've been attending during at the beginning of the week. So I'll just forward them to Dr. Mo to redistribute to everyone
Okay, fine.
because I
And
might not have the whole mailing list.
okay, fine. So Tafila, maybe also you can talk to Dr. Makos or whether people are interested in system dynamics or not. So if no one is interested, I think there is no need of me trying to prepare another lecture, for example, that we can look at fencing, for example, or system dynamics modeling in details. So just find out also from him whether this is possible or not.
Okay, yeah, I'll just also try to find out from the colleagues here who are online. Maybe they can show by raising their hands if they would want some detailed lecture on this topic. But I personally would want one. So if maybe, yeah, I think there's a good number of people who would want more information on that. So we
Okay,
can
then yes.
yeah, we can have and arrange our lesson for that.
Yeah, so fine. I think then I'm okay with that. I mean, we can arrange at some point where we can actually indeed just talk about system dynamics modeling, because we assume to say those who are interested, they're really into it, and then we can really have a, a candid discussion around that, and that where we can ask ourselves questions, we can tease each other, and or maybe work on a particular model and see how it works.
Yes, yes.
All right, colleagues. So yeah, if there is nothing more, I would say I wish you all the best. It's Friday, and I wish you a great weekend.
All right. Thank you. Bye.
Thank you so much.